Okay. All right. There we go. Of the forces on an object. All right, so we already know what free body diagrams are. We've kind of talked about them, but for the sake of making them easier, I didn't draw them exactly correctly. Like, for example, I said, if we're going to push something to the right, we're just going to push it like that to the right, remember? So we're going to see now when we're drawing free body diagrams properly, we're never going to have arrows pointing into the object. Every single arrow is going to originate from the center and out. So this would actually represent a push of 80 newtons. And then we would say this is the applied force to the right, okay? So that's the main difference between what I've showed you so far and how we're going to actually draw them. So no arrows are ever going to be pointing into the object, ever. They're always going to be originating from the inside out. All right, let me write the rules up here. So this is the way that we draw these. It's like a special example of vector diagrams. These are basically just vector diagrams. Remember that a vector has magnitude. And when we're drawing our free body diagrams, if I have a force of 10 newtons and a force of 100 newtons, I'm going to draw this one, the 100 Newton force, larger than I would draw the 10 Newton force. So we indicate the magnitude by the size of the arrow. Magnitude of force is indicated. And it doesn't have to be exactly to scale. Like this one, this 10 doesn't have to be 10 times smaller than the one that's 100, but you just have to draw one a little bigger and one a little smaller to indicate that this is a 100 Newton force that's larger than this 10 Newton force. So the magnitude of force is indicated by the size of the arrow. And then, of course, our second part of, well, hold on. Our second part of a vector is direction, and that's just direction. That's just indicated by which way the arrow is pointing. Indicated by which way the arrow is pointing. All right, so those are the two main pieces of our free body diagrams. We should kind of already know that. Okay, Yusra, you can come in, but you don't get any points. All right. So the rules. Let's make sure we have our rules so you know. So every time you draw the free body diagram, rules, and I'm going to call them like, I don't know, rules or the components that you need. To properly draw the free body diagrams. So we have obviously our box in the center, and this is our object. We already know that. That doesn't change. We have an arrow with magnitude plus direction for each force being applied to the object. And we also must have a label on each arrow. And this is where the last section is going to come into, you really need to know all those different types of forces, like all the contact and non-contact forces that we discussed. You have to know them because you're going to have to be able to label them. So like I just had this one up here with 80 newtons, and this was F applied. You have to label them every time. So you can rewrite the value, the magnitude, plus under that you will write, or to the side of that, whatever, you write the type of force that it is. So there's also a force of gravity. Let's say we would have to write what that is. I don't know, I'm just making this up. This would be the normal force. And this would be the friction force. Whoops. F friction. Okay. So, and then a value, and a value, right? So you have to be able, you have to label each of them. Don't forget that. And that is it. Those are the three components that you must have for every single one to get full points on, and to get it correct, more importantly. Okay, so let's do the examples from the homework real quick. Does anybody have any questions so far while I pull up the homework? Uh-oh, why does it do that every time? Does anybody have any questions? You can ask, just to unmute yourself and ask if you do. And I'm gonna pull up the homework. All right, fine. Okay, so the first one says that a box rests on a countertop. So I have my box. I'm not gonna draw the actual box. I'm gonna just draw the free body diagram. I have a box resting on a countertop. Draw the free body diagram of all the forces acting on the box. All right. Anyone want to tell me one of them?
Gravitational force.
Yep, force of gravity would be down, and we don't have any values for any of these yet, but we will get values for them, but not yet. So right now we're just going to label them. Yep, force of gravity. Any other forces?
Normal force.
The normal force, which is in the opposite direction, going up. Are there any others? Nope. That's it. So that was the answer for the first problem. This was, I don't remember, this was on Tuesday, the Tuesday assignment, I think. Okay, then it says an egg is in free fall from a nest in a tree and air resistance is negligible and may be ignored. And draw a free body diagram of this egg. So the egg will be my box. So what are the forces acting on the egg?
Isn't it just gravity?
Isn't it just gravity? Yep. That's it. If air resistance was not negligible, we would draw an arrow up here. But in this case, it's when an object is falling at a really short distance and the object is very tiny, like an egg, we don't think about air resistance because it's there, but it's like super tiny. It would barely change our value, so we don't care about it. All right. Then it says a rightward force is applied to a book in order to move it across a desk with a rightward acceleration. So here's my book. What are the forces acting on the book?
Force of gravity.
Force of gravity going down. Yes. What else?
Friction.
Friction force would be going this way, right? Since we're moving rightward.
And the applied force on the other side.
The applied force, and we don't know the magnitude, so I know that it would, well, it's moving. Yeah, you wouldn't know that yet. So anyway, we'll just do this. F applied, and is that it?
No, normal force.
The normal force also. Exactly. When you're drawing the normal force and the gravitational force, try to get the arrows. I didn't get them very exact. Try to get should the arrows have a magnitude that is exactly the same? Do you know? What do you think?
Is it moving or not moving again?
Well, just between the normal force and the gravitational force here.
They should be exactly the same.
They should be exactly the same because the box, or is it a book? Whatever it was. The book is not falling through the table, right? So they should be exactly the exact same magnitude, right? If it's moving to the right though, which force do you think should be bigger? The friction force or the applied force?
The applied force.
The applied force, exactly. So that arrow should be a little bit larger. Okay. All right, we have two more and then we're done. We have a football moving upwards towards its peak after being kicked by the punter, and air resistance is negligible and can be ignored. So here's my football. What are the forces acting upon it?
Gravity.
Gravity. Anything else?
applied force.
We already applied the force. Is when the football, so what happens is the guy is right here and he kicks the football and then the football travels up and now it's right here. This is where we're talking about the football. Is there a force? Is there applied force on it? There was one right here, but now there's not one any longer at the top of the peak. There's no applied force. There's the football, the guy's foot doesn't stay on the football the whole time, right? It's once his foot kicks the ball and the ball leaves his foot, there's no longer an applied force. Do you understand that, Yusra? I think that's you who's talking.
Yeah.
So do you understand
So it's
what I mean?
just gravity by itself.
Yeah, there's nothing else. There's no friction force. There's no air resistance. It's only gravity by itself. So this is correct. This one right here. That's the correct.
I don't understand.
Okay, what part don't you understand?
I mean, yeah, it did, like, it's not touching the foot anymore, but how did it get up there? Because it still has the applied force. If it was just gravity, wouldn't it be like the falling down part?
It is falling. It's falling. It's going to be falling.
Okay.
It's going up and it's going to come back down. That's the only force that's acting on it. That's why it gets to the peak and then falls, basically. You understand? There's no longer a force applied to it. If the force was applied, if there was a force applied to it still, it would be this way. If there was still an applied force, that football would continue in the same direction forever. If his foot never left, if we continued applying the same force, it would never fall. Do you understand? It's kind of an abstract concept, I know. It's kind of weird to wrap your mind around. So it's like a brain exercise, but there's no applied force on it after the ball leaves his foot. Only the force of gravity. Okay? All right, your last one says that a car is coasting to the left and slowing down. Draw a free body diagram of this. Slowing down. Coasting means, I hope you know what that word means, otherwise this question is very difficult. Coasting means you're not pushing the brake, you're not pushing the gas, you're just letting the car roll until it stops. So what are the forces acting on the car? Anyone?
Gravity.
There's
Gravity?
sliding friction.
Yeah. Friction.
Normal force.
We don't have to say sliding friction because it's actually, technically this would be rolling friction because we have wheels, but we're not learning that because we learned that in 9th grade and it's just more complicated, but not more complicated, but there's already enough to go. So we just call it friction force. You don't need to verify that it's sliding friction. All right, there's one more.
And normal
force. Yep. Okay, well, that's pretty easy. Then I feel like you guys understand this stuff pretty good. So we're almost done with 2.1. So for homework, you're just going to read 2.1D. Tomorrow we'll do this same thing. And so what time do you have class normally then with me? Does this time work for you? Does 10 a.m. work for you? Is that okay?
Yeah, I guess.
Yeah.
Well, wait, Miss Montgomery, are we gonna be doing Zoom classes every morning?
Not every morning. No, not every morning, but like everybody.
So like we're doing a mixture.
We're doing a mixture, but we'll only do the video like if it's a review or something. I guess I don't know yet. I haven't decided yet, but like for this new information, this is like, it's way easier, and I'm having problems uploading videos also. So it's way easier for me and for you to get the information this way, because then you can also ask me questions. So
Okay.
I will do some recorded lectures, but I'm not sure when or where yet. So maybe like once a week, and then 2 or 3 times a week we'll do a Zoom meeting. That's what you all wanted.
Not me.
Oh, well, I'm sorry, Lena, you're not the center of the universe, bro. Okay,
Really,
so
I didn't know that.
we're going to do you have stop sharing here. All right, you have homework. You're going to read 2.1D. I'm going to stop my recording of this also. Okay, anyway,